Hi, I'm Herb Gross, and welcome once again to Gateways to Algebra, where we're doing our 36th lecture, and today we're going to apply the things we talked about in terms of graphing solutions to equations. We're going to talk specifically about solutions to quadratic equations in terms of graphing. And to get into that, let's just review with a simple enough problem that doesn't require any kind of graphing at all. Suppose we just have the problem, solve x squared minus 4x minus 5 equals 0. See, there's a typical quadratic equation. We don't need the quadratic formula for it, even though we could use it. What we're looking for is what? Two numbers which when multiplied together give me negative 5, but which when added together give me negative 4. That would be negative 5 and positive 1. So x squared minus 4x minus 5 equals 0 can be written as the product of x minus 5 and x plus 1 equaling 0. Since the only way a product can equal 0 is for one of the factors to be 0, it's either x minus 5 which has to be 0 or x plus 1 which has to be 0, in which case if x minus 5 is 0, x is 5, and if x plus 1 is 0, x would be negative 1. Now, what we're talking about is, instead of solving the problem this way, suppose we didn't know how to do that, couldn't we instead have simply graphed y equals x squared minus 4x minus 5. And once we had this graphed, all we would have to do is look to see where y is 0. Y is 0 every place on the x-axis. So in other words, the graphical solution of this equation would simply come from doing what? Drawing the curve y equals x squared minus 4x minus 5, and then seeing where it crossed the x-axis. And the beauty of this approach is that it's much easier, given the form y equals x squared minus 4x minus 5, to start with x and solve for y than it would be to start for y and solve for x. And the usual way that we make graphs, at least at the pre-calculus level, is that we sketch certain points, and once we have enough points that we feel comfortable with how the curve must look, we then fill in the intervening spaces. So to graph y equals x squared minus 4x minus 5, I would pick various values for x, and just to make things easier, I'll just pick x to be whole numbers for the time being over here. See, notice I've left out negative numbers, I've left out fractions, but I can pick any value of x I want. You see, I can take any input, and for that input all I have to do is what? Square it, subtract 4 times the input, and then subtract 5, and that will give me the output. So what I'm going to do is I'm going to have an x column, an x squared column, a 4x column, an x squared minus 4x column, and then I'll subtract 5 from that to get the y column. So what happens over here? When x is 0, x squared is 0. 4 times x is 0. Hence, x squared minus 4x is still 0. And hence, x squared minus 4x minus 5 would be negative 5. And since that's what y is, see, maybe I should put this down here just so that remember what's happening over here. See, in other words, the y column is always going to be what? 5 less than the x squared minus 4x column. So when x is 1, x squared is 1. 4x is 4. Okay, so, and then x squared minus 4x is minus 3. Okay, and then y would be negative 8. When x is 2, y squared is 4. 4x would be 8. So x squared minus 4x is negative 4, so y would be 9. And you see what's happening? I'm getting points like what? We always write the x coordinate first. So 0, comma, negative 5 is 1 point on my graph. 1, comma, negative 8 is another point on my graph. 2, comma, negative 9 is another point on my graph. 3, comma, negative 8. 4, comma, negative 5. Okay? And 5, comma, 0. And by the way, all we do to do this now is what? We take those points and locate them in the xy plane here. So 0, comma, negative 5 means you're on the y-axis, but 5 units below the x-axis. 2, comma, negative 9 means that you're 2 units to the right of the x-axis and 9 units down. 1, comma, negative 8 means you're 1 to the right and 8 down, and we just keep going like this. And you see, these are the points that we have. By the way, the reason I dot this, and this will explain why calculus is important, that one of the things we don't know is, and we've mentioned this before, as long as there are spaces here, it's possible that crazy things happen. See, we don't know. See, we don't know where this curve is going. It's just that based on what we see, it seems quite likely that the curve is probably going to be doing something like this. But I thought that what I'd like to show you is how algebra can take the guesswork out of what's going to happen over here. Let's go back to the graph y equals x squared minus 4x minus 5 and use some of the stuff that we now know about completing the square. See, forget about the minus 5 over here. What do you need to complete the square if you have x squared minus 4x? Remember what the rule was? Take half of the multiplier of x. Well, half of negative 4 is negative 2, and then square that. And negative 2 squared is 4. Now what are we going to do? We're going to add 4 on here to get a perfect square. But we don't want to change anything, so if we add 4, we also have to do what? Subtract 4. You see what happens here? This becomes x squared minus 4x plus 4, and we'll put that in parentheses to emphasize that we want that by itself. Then this is minus 4 minus 5. Well, see, x squared minus 4x plus 4 is a perfect square. It's what? X minus 2 squared. And minus 4 minus 5 is minus 9. So another way of writing this in terms of completing the square is that y is equal to x minus 2 squared minus 9. Now, you may ask, why is it so important to go from this form to this form? And the answer is, in this form, we have a perfect square. And what's important about a perfect square? As long as we're talking about real numbers, a perfect square can't be any less than 0. Remember again, negative times negative is positive, positive times positive is positive, 0 times 0 is 0. So the square of any number, any signed number, has to be at least as big as 0. So in other words, what can we say for sure over here? This number has to be at least as big as 0. And if I subtract 9 from a number that's at least as big as 0, the smallest I can possibly get is negative 9. See, in other words, what is the smallest that x minus 2 squared can be? The smallest this can be occurs when x minus 2 is 0. But the only time x minus 2 can be 0 is when x is 2. And what happens when x is 2? When x is 2, y is negative 9. Now what this shows me is that not only is 2 comma negative 9 a point on the graph, but it's what? It's the lowest point on the graph. In other words, y is least when x minus 2 squared is 0, and that in turn happens when x is 2. When x is 2, y is negative 9. By the way, notice you can get the same thing here. If x is 2, 2 squared is 4, 4 times 2 is 8, 4 minus 8 is negative 4, negative 4 minus 5 is negative 9, but look how much easier it is to do here, because as soon as x is negative 2, this whole term drops out, and you're left with y equals negative 9. So the important point is that 2 comma negative 9 is the lowest point on the curve y equals x squared minus 4x minus 5. So you see, what that tells me right away is that if I want to graph this particular curve, in other words, if I want to draw y equals x squared minus 4x minus 5, what I do is I go down to the point 2 comma negative 9, and what do I know? That's the lowest point on the graph. That's the minimum. So it means what? Just on one side of the curve, I must be above this point. On the other side, I must be above this point. That means the shape is something like this. And now you see I can project that this thing is just going to keep on going. And you see I can also project that this curve is going to look exactly the same. If I put a mirror on the line x equals 2, what I see here will be the mirror image of what's over here. And the reason is, notice that when I square x minus 2, it makes no difference whether x is 1 unit less than 2 or 1 unit more than 2. In other words, when you square, all you're taking into consideration is the size. See, for example, let's go down here. Here's 2. 1 unit to the right of 2 would give me 3. 1 unit to the left of 2 would give me 1. So it doesn't matter whether I'm talking about x minus 2 or whether I'm talking about 2 minus x. In other words, x minus 2 would look like this. 2 minus x would look like this. But you see, these are both what? The same distance from 2. So what this says is, whatever the curve looks like on one side of the line x equals 2, it'll look exactly symmetric with respect to the line x equals 2 on the other side. So this basically becomes the typical size of a parabola. Now, how wide the parabola is, you see how wide the parabola is, where the lowest point is or where the highest point is, that depends on the numbers a, b, and c, and we can go into that later. But the thing that I wanted to point out is that notice that how many solutions there are to a quadratic equation once you've drawn the parabola depends on where the x-axis is. In other words, if the x-axis were over here, suppose this is the parabola. Here's the thing I want you to notice. The shape of this parabola is the same no matter where the x-axis is. But if the x-axis is over here, do you see that there are going to be two solutions? Because the x-axis cuts the parabola in 2 points. Okay, what happens over here? Only 1 point. And what happens down here? No points at all. In other words, if the x-axis is over here, this is an example where there are 2 solutions. If the x-axis is over here, there's 1 solution. And if the x-axis is over here, there are no solutions. And let me just show you one more thing this way. You see, the reason I bring this up is, once I draw a parabola, let's just abbreviate this by y equals ax squared plus bx. Okay? And by the way, if I did it this way, if y equals, in fact, let me do that over again for you, just so you don't get any kind of an optical illusion over here. If y is equal to ax squared plus bx, notice that when x is 0, y is 0. And let's suppose a is positive, so the parabola looks something like this. Now, what happens when you tack on c? Remember we showed that the relationship between f of x and f of x plus c was that adding on c just raises or lowers the graph. In other words, if c is positive, this picture gets lifted by c units, and if c is negative, it drops by the magnitude of c units. So what happens is, if this is where the curve is over here, if I make c positive, that's going to make this, it's going to take the same picture and move it up. And that means it's not going to cross the axis at all. If c is negative, it drops the parabola, and that's where you're going to get 2 solutions. So that's what we're trying to show when we said that how many solutions you get depends on where the x-axis cuts the parabola. Okay? So for example, suppose I now took the equation x squared minus 4x plus 5 equals 0. Let's see what happens here. I want to complete the square, so I add on 4. See, because half of negative 4 is negative 2. I square negative 2, that gives me 4. If I add on 4, I have to subtract 4. So now I have what? X squared minus 4x plus 4, which is x minus 2 squared, just the same as before, plus negative 4 plus 5. Well, see, that's now positive 1. See what the difference was? I just changed the sign here from the problem we did before. This was a negative sign. I've now made it a positive sign. You see, in effect, what I've done is I've taken that parabola that was down here, and what I've done is I've gone from a c value of negative 5 to a c value of positive 5, and what that has done is it's lifted the parabola up. And now that parabola is no longer cutting this axis. And see how that manifests here? See, we get what? X minus 2 squared plus 1 equals 0. And that's impossible, because you see, by virtue of being a square, x minus 2 squared has to be at least as big as 0. If you add 1 onto a number that's at least as big as 0, the answer has to be at least as big as 1. So how can this expression possibly be 0? There are no solutions here. And again, if you wanted to draw this, see what this thing says? Let's just copy this over. See, what we showed was that if you want to graph y equals x squared minus 4x plus 5, by completing the square, by adding and subtracting 4, this became x minus 2 squared plus 1. And by the way, if you want to check this out, just square this out. It's what? X squared. The 2 times the x is 2x, times 2 is 4x, but it's a minus sign, plus 4. Then you add on the 1, and there's your x squared minus 4x plus 5. So what we're seeing here is what? This is going to be the least when this is 0. This will be 0 when x is 2. When x is 2, this drops out, and y becomes 1. And what that tells me is that the lowest point on this particular parabola that's what it's called, the parabola, is 2, comma 1. In other words, I go 2 to the right and 1 up, and that's the lowest point. That means the curve is rising on this side, it's rising on this side, and therefore can this curve ever cut the x-axis? No, it can't. By the way, I did mention that, how should I mention it? When this is positive, the parabola looks like this. When the coefficient of x squared is negative, something different happens, and we should point that out. Let's see if we could graph y equals 6x minus x squared. But now the way I want to graph this is by having you use just algebra and not worry about the picture. See, if y is equal to 6x minus x squared, to make this positive, I will just factor out a negative 1. In other words, I'll change both of these signs and put a minus outside. See, I'll take minus the parentheses x squared minus 6x. Do you see that? See, if the minus really means minus 1. Minus 1 times x squared is negative x squared. Negative 1 times negative 6x is positive 6x, so this checks out. Now to complete the square here, I do what? I take half of the negative 6. That gives me negative 3. I square that, gives me 9. But if I add 9, I also have to subtract 9 so I don't change anything. So the minus sign is still outside here. What's left inside the parentheses? It's x minus 3 squared minus 9. The negative sign outside the parentheses changes these signs for me. The negative 1 multiplies the negative 9 to give me 9. The negative 1 multiplies x minus 3 squared to give me minus x minus 3 squared. And now do you see what's happened? Now the thing that's being squared is being subtracted from 9 rather than 9 being subtracted from the x minus 3 squared. You see, now when you're subtracting, the least you're subtracting is 0. In other words, to make a number bigger, see, what's the biggest you can have? When you're subtracting, the biggest you can have is when you subtract the least. But the least you can subtract over here is what? 0, and when will this be 0? When x is 3. But when x is 3, this drops out and y is 9, so now we know what? The highest point on this curve is 3, comma 9. In other words, if you went to graph y equals 6x minus x squared, if you actually located the points this way, there may be a little bit of doubt, but the point is we now know what for sure by the algebra. We know that the highest point occurs at 3, comma 9. Now, it's difficult sometimes for people to solve these particular problems, so there is a trick that we do. Rather than keep graphing all these different parabolas, I thought I would like to show you one little trick that you might like to think about. You see, when I write down ax squared plus bx plus c equals 0, let me solve this for x squared. In other words, I say what? Ax, subtract bx and subtract c from both sides. So this will drop out here. What do you have? Ax squared equals negative bx plus negative c. Now you can divide both sides of the equation by 1 over a. This will leave x squared on this side minus b over ax plus minus c over a on this side. Now here's the point. Think of the x, this says two values are equal. Think of this as being the curve y equals x squared. And think of this as being the straight line y equals negative b over ax plus negative c over a. What that line will look like depends on the choice of a, b, and c. But the nice part is that the parabola on the left-hand side is always going to be y equals x squared. So once you draw that parabola one time, you never have to draw it again. You can trace it out, keep it, and now what are you going to do? To find out what the solutions of this equation are, what you're going to do is you're going to take the line y equals minus b over ax plus minus c over a, draw that line. And wherever that line crosses the parabola, the x values will tell you the solution of this equation. For example, let's take another problem that we know the answer to. We know that x squared minus 3x plus 2 equals 0 can be solved by writing this as x minus 2 times x minus 1 equals 0. And then the solutions are what? Either x minus 2 is 0 or x minus 1 is 0, so either x is 2 or x is 1. The graphical way of solving this, if you only want to use the parabola y equals x squared, which I've dotted here, you say what? If I put it into this form, this says what? X squared is equal to 3x minus 2. How do I draw the line y equals 3x minus 2? The y-intercept is negative 2. The slope is 3, so it means I go 1 over and 3 up. I draw this line, and wherever this line cuts the parabola, the x-coordinate of those points tells me the values I'm looking for. See what happens over here? This is the point 1, comma 1. This is the point 2, comma 4. So what is the solution to this equation? X equals 1 and y and x equals 2. Another way of saying it is that these two curves, y equals x squared and y equals 3x minus 2, meet in 2 points, 1, comma 1 and 2, comma 4. And what this does is it gives us a new way to look at what the solutions of a quadratic equation are just by looking at one parabola. See, here's this one parabola. It's what? Y equals x squared. What are the three possible things that can happen if I draw a straight line? Well, one thing that can happen is the straight line cuts the parabola in 2 points. See, 2 solutions. Another thing that can happen is the straight line is tangent to the parabola. It touches it at just 1 point. There's one solution. And the third situation is what? The straight line misses the parabola altogether. In other words, this parabola is rising like this. This straight line is moving out like this. This straight line will never meet this parabola. That corresponds to no solutions. Now, I think this is a good place to stop. It's been like one long piece in this particular situation. But every so often, we're going to come to a topic that doesn't really require as much explanation in terms of you seeing me as it does just to see the writing and the manipulations that take place. What I'm hoping that you're starting to see is a great balance between arithmetic, in other words, analysis, and geometry. You know, it all begins, I don't know if we ever mentioned this earlier in the course, but you know, as soon as you've seen a ruler for the first time, that's the beginning of the unification, the marriage of arithmetic and geometry. After all, what is a ruler? A ruler is a straight edge, that's a geometric concept, on which you mark off points at regularly spaced intervals. Points are also geometry. But what do you do to those points? You name them numerically. You call them 1, 2, 3, 4, etc. So what have you done? You've identified geometric concepts called points on a line with arithmetic concepts called numbers. So what's going to happen very, very often in math is that if you're trying to solve a pictorial problem, if you know the analysis, you can translate the picture into an algebraic equation and use the algebra to solve the problem. On the other hand, if you have a difficult algebraic problem, but you can represent the problem pictorially, what you do is what? You draw the picture, and for example, if it's the equation f of x equals 0, you simply draw the graph y equals f of x and see where that graph cuts the x-axis. It's a computational device that hopefully will get you to think of algebra and geometry interchangeably. At any rate, that concludes our study of quadratic equations, but one of the things that came up that I think will occupy us for the remainder of this course is a strange idea of why should a quadratic equation not have solutions just because it doesn't cross the x-axis. In other words, somehow or other, when you see a second-degree polynomial, you expect 2 answers. And just because the graph doesn't cut the curve, cut the axis, doesn't mean in your own mind that there shouldn't be any answers. So I want to show you in the next few lectures something which to me is very, very profound, and it shows how the human mind can conjure up all kinds of new inventions when we arrive at a crossroads where the previous information is insufficient for us to pursue our investigations. But we'll talk about that gradually throughout the next 4 lectures. But until then, study hard, be happy, and stay young. Talk to you soon.